Why is the sim-to-real gap a challenge for RL applications? Imagine training a robot in a computer simulation that looks and feels just like the real world. Now picture sending that robot out into the actual environment. What do you think might happen? The robot might stumble or behave unpredictably. This is because of what experts call the sim-to-real gap. The sim-to-real gap is about the differences between the virtual world, where reinforcement learning agents are trained, and the real world where they are put to work. Reinforcement learning involves teaching an agent to make decisions by interacting with an environment and learning from rewards or penalties. Simulations are great because they let us train quickly, safely, and without risking damage. But they are never perfect copies of reality. In simulations, sensors might be idealized, and physics can be simplified. Lighting, textures, and environmental factors are often not as complex or variable as in real life. For example, a robot trained in simulation might learn to walk perfectly on a flat, smooth surface. But when it encounters uneven terrain or noisy sensors in the real world, it might struggle. This mismatch causes what is called a distribution shift. The data the agent learned from in simulation differs from what it faces in reality. Because of this, the agent's policies might misinterpret real-world inputs or make poor decisions. It might rely on features that do not exist or behave differently outside the simulation. Another problem is overfitting. When trained in a simulation, the agent might become very good at handling the specific conditions it was trained on. But real environments are more variable. This makes it hard for the agent to generalize and adapt to new or unexpected situations. Training directly in the real world is often too costly, slow, and risky. Robots can get damaged, or the environment can be disturbed. So, researchers try to bridge this gap with techniques like domain randomization. This involves changing simulation parameters randomly during training, so the agent learns to handle a wide range of conditions. Other methods include domain adaptation, where the agent's perception is adjusted to better match real-world data. Sometimes, training is done into stages, first in simulation with extra information, then fine-tuned with limited real-world data. Combining virtual environments with real sensors or dynamics also helps. Understanding the sim-to-real gap is important because it shows why applying reinforcement learning outside controlled simulations is challenging. It highlights the need for better simulation fidelity and training strategies that make policies more robust. When AI tools like ChatGPT or DALL-E operate mainly in digital worlds, they don't face this physical gap. But for RL agents working in the real world, closing this gap is key to making them reliable and safe. In essence, the sim-to-real gap makes it difficult for trained reinforcement learning agents to perform well when they move from virtual training to real-world deployment. Overcoming this challenge involves improving simulations, training methods, and adaptation techniques to ensure these agents can handle the real environment's surprises.